To be with you is easy. I know you're good for me.
Hello, I'm Professor Caudill, and we have come to the end of the chapter. So, I think the biggest thing that I would want to recover is so we have a theory, and that theory is made by a set of laws. And each law in our theory, let me read that on the next line. For all laws in our theory, there exists a combination of quantities, and that's one, and that's up to 7 quantities. And these quantities will describe actions by the law. So why is this important for the AI to see? So in the automation I've done, I take one action to one action, and I convert it into a one action. I'll put in actions. It could be in could be 3, or it could be like a while loop, like the I think what I showed you in the welcome video. I took a script where it turns the left mouse click 1-to-1 action into a 1 to infinite action. Well, not it's 1 to however long the left mouse button is pressed, but as long as the left mouse button is pressed, it continuously clicks. So it's a 1 to n action, and what that results is performance boost. So that's kind of reiterating why we're here. So summary, see physics about laws. Scales are important. Magnitudes help you estimate and get a better approximation. Usually just knowing the order of magnitude of quantities you're talking about is good enough. So quantities, your measurements are defined by how precise your measurement tool is, how competent the scientist is, and how well defined the standard of measurement is. So in this book, we're going to be focusing on length, mass, and time. So we tend to use a metric system. Unit conversion, this is very hard. It was very, very hard for me, probably the hardest part of this chapter. All equations, especially physical laws, must be dimensionally constant. So you have to check to make sure you're not violating the rules of dimensions. Estimates and Fermi calculations, get big lengths from small lengths. Round it. Ask yourself, does it make sense? Kind of rules of thumb. Significant figures. Not sure what else to say here. yeah, you can't have more decimal places than what the grade of the tool is. And overall, use strategy, solution, significance. What physical principles are involved in our automating task, and figure out um, you know convert the interactions of the physical principles you want to automate, convert it into math. Check the solution, make sure it makes sense, and all right. So let's get into some problems. We got quite a few problems here. It'll probably take us a couple of videos to get through these. Looks like there's 100 problems, including challenge problems. And then our next chapter is vectors. So we'll probably try to do most of these. Like anything, the basics. If there's anything more important, it's usually the basics. One more thing. So since we're not a normal school, we'll probably just try to solve it as fast as can using all our tools in our toolbox. We're not going to take a moral high ground and limit ourselves by avoiding using AI or anything silly like that. We're gonna approach these questions like a real world problem. That means using everything we got to try to answer them. So find the order of magnitude of the following physical quantities. All right, so mass of Earth's atmosphere. All right, 5.1 times 10 to the 18. So, if I recall, the book, it said 10 to the 0.5 is between 10 to the 0 and 10 to the 1, which is saying 3 is between 1 and 10. So the orders of magnitude. So obviously 5 is greater than 3. So we're going to say this is 10 to the 19. Now this is kind of counterintuitive to me because usually if it's 5 or greater, you round up. But I think this is what the book taught, so this is the answer I'm going to give. Alright, next is the mass of the moon's atmosphere. 25,000 kilograms. So that's 2.5 times 10 to the 4. Let's check our answer. 2.5. 1, 2, 3, 4. So 1, 2, 3, 4. So 1, 2, 3, 4. So what we get, 25,000. That seems to be correct. Kilograms. Not going to be too sticky on it unless it's absolutely required. Unless conversion is a factor. The mass of Earth's hydrosphere. So that I can just tell by looking, that's 10 to the 21. A significant figure is less than 3. Okay, the mass of the moon is going to be 10 to the 23. the Earth Moon semi-major axis. Okay, that's 10 to the 9. The mean Earth distance, again, 10 to 11. Um, what is H asking us? You know, the mass of an electron, mass of a proton, the mass of the sun, and then, okay, I see. It's formatted a little weird. Okay, equatorial radius of the Earth is 10 to the 7 meters. Mass of electron is, so this will be 10 to the negative 30. Trick here is we're adding 10 to the, we are rounding up, so we would drop down this, we would add by 1. Let's see, that's 10 to the negative 27 for mass of a proton, and the mass of a sun is 10 to the 30 kilograms. Alright, using the order of magnitude found in the previous answers, answer the following. Alright. How many electrons would it take to equal the mass of a proton? Basically, how many electrons are in a proton? So we take our mass of a proton, which is 10 to the negative 27, and we divide by 10 to the negative 10 to the 6, 10 to the 7, and that is 10 to the negative 27, and that's minus 7, and that's 10 to the negative 34 kilograms. Or, let's see, I'm sorry, 10 to the negative 34 electrons. 10 to the negative 34 electrons should fit in a proton. All right, now let's see. How many Earths would it take to equal the mass of the sun? So we're taking the sun, we're taking it divided by the Earth, and we know the sun is 10 to the 30 divided by the 10 to the 7, and that is 10 to the 23 Earths. It's a lot of Earths. So we started with masses. I think C is going to start with distances. So now we gotta kind of reset here. How many Earth-Moon distances will it take to cover the distance from the Earth to the Sun? So we know the distance from Earth to the Moon, and we want to use this length to calculate the Earth, the Sun. So we're going to take ES divided by EM and, or whatever the length is, the length, let's put it L, the length the length of the Earth and the Sun divided by the length of the Earth and the Moon. So that's what we're trying to find. So Earth-Moon distance, we have Earth-Moon distance. I think the semi-major axis is just okay, so I think the semi-major, it would be this line. Assuming like if we flattened the Earth, I think this is a semi-major. But let me double check. The horizontal line on the what is that called? On the center of the sphere, where the sphere is would be flattened, we get the distance across. So is that what I'm talking about? Semi-major axis is the Earth, refers to Earth, refers to half of the longest diameter of its elliptical orbit. It's not a measure. Earth is generally considered an oblate sphere. Okay, equatorial diameter. Equatorial diameter is the widest horizontal distance. Alright, so I just took a screenshot by accident. So this is wrong. We are looking for the equatorial distance. That's what I thought it was. So we know the mass of the Earth's atmosphere, mass of the Moon's atmosphere, mass of Earth's hydrosphere, the average Earth-Sun distance. Okay, so there's our key point. Average Earth-Sun distance is 10 to 11 meters. We're taking that divided by Earth-Moon distance. Okay, so I'm assuming it is 10 to the 9 because that's the only other distance they talk about. And ChatGPT just say that the semi-major was a celestial orbit. So I think that would be right. It would be like so in reality the Earth the distance between the Earth and the Moon, it's following a parabola. So it would be like flattening this parabola to a distance, I think. Anyways, I think it's 10 to the 2 meters. Or I think it's 10 to the 2. Yeah, 10 to the 2 meters. I would probably say for this one. Okay, and since it's faster to check with the language model than going to the back of the book, we can take this, copy it. Does it sound right that 10 to meters would be the answer to this? Not be correct for the distance from Earth to the Sun in terms of Moon-Earth distances. And it's like whenever I get confident, ChatGPT takes me wrong, and I know ChatGPT is wrong a lot of the times, especially when he's trying to when the language model is trying to do math. But I think I can catch most of it. Um, Average distance from the Earth to the Sun is at 1 AU, which is okay. So it's about 1.5 million. Okay, so times 10 to the 6, I think that's a million kilometers, which is 1.5 times 10 to the 6 times 10 to the 3 meters. It's 1.5 times 10 to the 9 meters, which is correct with this. So no, that's not right. Should be the other way, right? Um, yeah, the mean, the average distance. So okay, so ChatGPT is wrong. It's ordered by 2 orders of magnitude. Either the book or ChatGPT is wrong by 2 orders of magnitude because it's saying this is the distance between the sun and the moon. I mean, the Earth and the sun. And the book is saying that 10 to the 9 is the Earth and the moon. So it's saying Earth to the moon is 3.8 times 10, 3, 5 times 10 to the 3 meters. So 3.8 times 10 to 8 meters. Okay. I think I see where we messed up. I think we messed up here. This should be a 9, right? So 150, 0, 0, 0, 0, 0, 0. That is 1 times 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it should be 8. All right. So now, if we did this right, it would in fact be 10 to the 11 meters. And this would be, in fact, 10 to the 9. And I don't know why ChatGPT is saying I'm wrong. Maybe ChatGPT is wanting a more precise answer. I'm going to stick with my answer. 10 to the 2 meters. Let's see what how ChatGPT might calculate it. Therefore, to find out how many Earth-Moon distances it would take to cover this, divide Earth-Sun, so we did, 10, 11, by Earth-Moon, so we did, 10 and 9, is 3.9. Okay, if I converted and estimated the order of magnitude of the Earth-Sun distance to be 10 to the 11 meters and Earth Moon to be 10 to the 2 and the 9 meters. Wouldn't it be 10 to 2 What's the book? How many yeah. I see where the confusion might be. If you are approximating order of magnitude, you estimate this in the Earth to be 10. In this estimation, you get order of magnitude 10 to. Okay. Using uh is it correct to say 3.8 times 10 to the 8 meters is approximately 10 to 9 since 10 to the 0 is between 10 to 1, 5, 10 to the 1, or 10, 5 is 3, and since 3.8 is greater than 3, we may round up the order of magnitude. All right, so it's gave me two answers. I'm reading. I want to see which one is more persuasive before I choose one. Um, oh man, this is head splitting. Um, I think this makes more sense. If you have 3.8 meters, not accurate is to say it is 10 to 9. So intuitively, I side with this. From everything I know, I don't. Maybe I'm misunderstanding what the book was teaching because I would round down here. 3.8, I would just keep it 10 to the 8 order of magnitude. And I feel like this is a big deal. I don't want to do estimates being off order of magnitude. And then you should compare the midpoint between 10 and 8. Ah, yes. So this is what is intuitive to me. 10.8 is between this, it's between this, it's between this. So 3.8 is in the range between this, so it's not correct to round up to 10.9. For observation that 10 to 0 is less than or equal to 2, this is correct. But we're comparing 10 to 9, not integers. Alright, so I think from here on, I'm going to humbly disagree with the book. And we're going to say it's 10 to the 3 meters. It's the distance. How many Earth moons it would take. Alright. Let me full screen here. Clear this. Alright. Making progress. Man, we're already 30 minutes in. Time flies. How many moon atmospheres equal Earth's atmosphere? So We have the moon, we have the atmosphere, and we want to see how many of these would fit in Earth's atmosphere. So we have Earth. This is Earth atmosphere. We want to see how many moon atmospheres would fit in Earth. And obviously, we would subtract the orbit, the planetary So this is a picture illustrated, but the illustration, you need to know that we're removing the planetary body masses. All right, so what is our given moon atmosphere? So we're taking Earth divided by the moons. So we're taking Earth atmosphere. All right, 10 to the 19 divided by 2.5. So I think it's always, so it's 2.5 times 10 to the 4. So is approximately 10 to the 15. Moon atmospheres. Oh. Per Earth. Does that make sense? Does this make sense? That's how much weight is. So we have the weight. Earth's atmosphere has the weight of about 10 to the 15 Earth atmospheres per Earth. And this is obviously in kilograms, right? I want to check this. So 25000 is so 1, 2, 3, 4. Okay. I'm building intuition for doing this, I think. All right, so I'm a little unsure. I'm confident, but I'm equally unsure. And that's dangerous. So let's check. Is it a good approximation that there is 10, 15 moon atmospheres that 10, 15 moon atmospheres could fit in Earth's? It's considered near vacuum, okay? So that does make sense. If you're comparing a vacuum to something filled with not a vacuum, then 10 to the 15 makes more sense. So here, ChatGPT didn't give us the answer. It just strengthened our intuition that we are in the right direction. And not only is that faster than going to the back of the book and check the answer, it's probably even better than what the book would have suggested. How many moons would take to equal the mass of the Earth? All right, so we're taking the Earth. We're taking divide the moon again. So Earth's mass is 10 to the 25. Mass of the moon is 10 to the 23. So we are saying 100 moons in an Earth. Is the Earth, could one fit 100 moons in the Earth? So strictly using mass 181 times. So again, our intuition seems to be validated by ChatGPT. 81 moons within the Earth. That is very close to 100 moons. And I, again, it is easier to, because it's hard to visualize 81 moons. Like, who would think, oh yeah, 19 moons. That's a lot. That's a lot you've left out. But no, it's a lot easier just to say 10 of the 2 moons or 100 moons in the Earth. Yeah. So how many protons would take the equal mass of the sun? So sun over protons. So let's see. Sun. Sun, mass of the sun is 10 to the 30. Protons, 10 to the negative 27. So if you wanted to chop up the sun into protons, if you wanted to express the weight of the sun in protons, you would get 1057 kilograms. Of protons. So the book didn't exactly say you should reference material of a weight, but I think this is kind of useful. Like kilograms of what? Gold, kilograms of feathers. Um, so in the sun. Okay. That's a lot of weight. Let me check, make sure the weights are in the same. Okay. Use figure 1.4. All right. Let me open up something. Uh, 1.4. Okay, so it wants us to use this. Um, Control tab, Control Shift tab. All right. 20 minutes left. So let's clear our board. Let's clear our mind. So lifetime. So over heartbeat. So this is this will be time divided by time. So tab. All right, so heartbeat is 10 to the 0 seconds, and length of one lifetime 10 to the 9 seconds. Okay. So seems pretty easy. Obviously you do 10 to the 9 minus 0, which is still 10 to the 9 seconds. Obviously what this is saying is your lifetime ends. Your lifetime is intricately defined by your heartbeat as of now. Until we transcend the limited human body, this won't be true anymore. Instead, it would be lifetime would be defined by some thermodynamic quantity of energy dissipation that provides information and energy exchange. So that's what I hypothesize. So now a generation is about 1/3 of a lifetime. So what is it saying? A generation is 10 to the 9 over 3, which is 10 to the 3 seconds is a generation. How many generations have passed since the year 0? So we're taking the year 0, which is 10 to the something seconds. Since year 0. So year 0 is recorded human history. So we have 1011 divided by 10 to the 3. That's 10 to the 8 seconds. So I want to convert this into days, and I take 10 to the 8 seconds divided by 10 to the 5. That's 10 to the 3 days. How many years is that? Okay, so we know there's 10 to the 8, so it'd be 10 to the 7 equals 10. So maybe we can't do this. Maybe we can't. is 10, 9, divided. I don't think I can do this. Divided by 3 equals to 10 to the 3. I don't think that's right. Yeah. That's a very bad mistake. All right. So I understood why it was wrong because I tried to convert it and I got 10 years. And I was like, okay, some calculation's wrong because what I just erased was saying 10 years is there's how many generations there's been. So let's restart. Okay. So lifetime is what, 10 to the 11 seconds? 10 to the 9, okay. So we're taking, that's a lifetime. And, we got this backwards. So we're taking record of human history. All right, we're going to take 10 to 11 seconds, record of human history divided by 10 to the 9 seconds, and that's going to be, all right, so what is it saying? 1/3 of 10 to the 9 is 1 generation. All right, so another way of saying this is 1/3 times 10 to the 9, or yes. And we're going to estimate this to still be 10 to the 9. I'm having trouble. I want to just write 10 to the 9. But I'm not 100% sure. Say human history is 10 to the 11 seconds and a lifetime is 10 to the 9. By estimating orders of magnitude, what would 1/3, and assuming a generation is 1/3 a the length of a lifetime, then how many lifetimes have have there been in recorded human history? I want to see how this does it. So it seems to be agreeing with me. I'm not exactly happy about it. Maybe that's my tendency for precision. So yeah. So ChatGPT basically said, okay, 1/3 times 10 to the 9. This is less than 5. This is way less than 5. is way less. How do you do the, I think it's much less than like that. Is much less than 5. Therefore, it's 10 to 11 or 10 to 9 equals 10 to 2, 100 generations. So, how many times longer than the mean life of an extremely unstable atom is it compared? All right, so how many? So we're dividing 10 to the 11, 10 to the 9 seconds of for a human lifetime divided by okay, so I need to know atomic nucleus time. That's 10 to the negative 22. Okay. So that's going to be 10 to the 9 minus 22, which is plus. That's 10 to the 31 seconds. So that's the length. That's how many how many lifetimes of an atomic nucleus are in one human lifetime. So does this make sense? Does it make sense? That there is 10 31 seconds worth time, assuming that is 10 to the 9, and the time of the atomic nucleus. Uh, 10, where did they get 10 to 53? 10, the total estimate time represented. Okay, yeah, that's what I got. Okay. So, yes, it makes sense. 10 to 31 seconds is 10 to 21. So, it's very, I think this makes a little sense. So, it's basically when you get this number, this human lifetimes per nucleus, you want to know how many lifetimes this is. You take 10 to 31 divided by 9, 10 to the 22 human. So this is not seconds anymore. This is human lifetimes. Okay. 10 to the 31 divided by 10 to the negative 22 is 10 to the 53. So let's see. If I cut human lifetimes into the lifetime of atomic nucleuses, we get 10 to the 31. Then if I take 10 to the 31 divided by 10 to the 9, we get either 10 to the 22 human lifetimes or 10 to the 53 human lifetimes. So I don't know. These don't really make sense to me. I'm sure they might to someone else. I'm gonna stick to this answer. 10 to 30, 31 seconds is the length of time. I think it's just time might be a little harder for maybe me to intuit and length or mass. I think that might be the reason for this. Why that one's a little more difficult. So we have 3 minutes left. Let's see if we can get through the first page. Number of atoms in bacterium. Assume the average mass of an atom in bacteria is 10 times the mass of a proton. So we want to calculate number of atoms in bacterium. So we're taking bacterium divided by atoms. We're going to get this number. And we can assume bacteria is 10 times the mass of a proton. So we're doing mass. We know the mass of bacteria is 10 to the negative 15, and we're dividing it by the mass of an atom. And they don't give us the mass of that number of atoms in a bacteria. They don't give us the number of atoms. The average mass of an atom in bacteria is 10 times the mass of a proton. So it is, so atom is 10 times the mass of a proton. Maybe we're just use 10 to the negative 26. So 10 to the negative 26. That is 10 to the negative 15 minus plus 26. That is 10. 10 to the 11 atoms. Okay. Bacterium. Kilograms worth of does it make sense? There are 10, 11 kilograms worth of atoms in a Okay. So yeah, 10 to 11 kilograms is a lot for a very tiny thing. Okay, so ChatGPT clearly says I'm wrong, so next time we will give another attempt at problem 19. And we're gonna leave off there, so thank you guys for watching. I'll see you next time. We'll pick back up where we left off.